knowledge with regard to Internet of Things, other challenges to the Internet as we know it. I think we have lost a lot of time. Without further ado, maybe pass the mic to. Thank you.
Okay, again, being too noisy. Again, thank you so much for coming and your patience. Well, we were having some pre-Internet of Things problems, so I appreciate your interest. What I wanted to do today is give you a perspective, personal perspective, on a very broad topic that you hear a lot about. Everybody talks about the Internet of Things, probably along with 5G is kind of the most buzzwordy part of communications right now. And we don't always do a good job, I think, collectively of distinguishing what we're really trying to talk about, and that there are really many different problems and issues, not just there is no single Internet of Things. So what I want to do is give you a perspective in the time available. I won't be able to go into every possible topic, and I hope that we'll have some time afterwards for you to maybe voice your opinion or ask questions as you want to discuss items. So let me get started saying the Internet of Things is actually not a single technology in my view. It is actually a combination of technologies that were all available at roughly the same time, starting maybe 2-3 years ago, that you had these suddenly available mechanisms that wouldn't have made Internet of Things possible if these individual components weren't available. So let me go through those, because each one of those contributes vitally to this thing that I'll define a little bit more as we go along. So the most important one, in my view, is that we now have systems on a chip that integrate typically a processor, ARM processor, or something like that, memory, and importantly, communication facilities. It used to be that you could buy an Intel processor, and then you would have to buy an Ethernet adapter and a Wi-Fi or Bluetooth chipset, and so a board consisting of a communication one was basically a little PC. It would cost you several $100s before you had a functioning network component. Now you can buy a chipset that does it all in one. The second piece is, and that's an important one, is that we now have mature Internet protocols. We've had Internet protocols obviously for 30 plus years, but they were hard to use. There was libraries available. It didn't work all that well in many cases. But now pretty much all of the standard protocols that we use, IPv6, TCP, HTTP, are all pretty solid. They've been well tested. The software implementations are well tested, and so on. So we now have a solid foundation, protocol foundation to build on. And importantly, tying back to the previous point, is it used to be that these really small microcontrollers were not capable of implementing a full IP internet stack. Many, many years ago, before there was an Internet of Things, as when I was a graduate student, I worked on a controller for a printing press. I designed a printed circuit board. I used a microcontroller. I don't know if any of you might remember, it's called an 8051 8-bit microcontroller, and it was trying to set up network communication. It was impossible. I mean, there was not enough memory, the processor wasn't fast enough, there was no real operating system you could use, so it was really difficult to build a networked controller, what I wanted to do. That's now quite easy for many cases. For wide area systems, we have now pretty good, in most countries, pretty good cellular connectivity, certainly 2G, some cases 4G, that makes it possible to deploy systems across a country pretty universal. And obviously we have unlicensed that makes it cheap and easy for many households and companies to deploy the Internet of Things inside their home or their office. Again, 10 years ago, that would have been very difficult. You would have had to set up a separate system. If you had a communication system outside, you would have had to use a VSAT or something like that. No longer, generally speaking, necessary. Next, we actually now know what we can do with data. Big data clearly has been a hot topic as well. The ability to analyze large sets of data that we can now use not just to do direct control loops, but also to utilize data much more effectively. Not so much that techniques are new, but they're now tools that you can just use, ready-made tools that allow you to do analysis on that. Machine learning tools, big statistical tools, and so on. We obviously have applications. It's now much easier to write applications than it was, again, 5-10 years ago. It's not hard to write a web application, for example. There's now good tool sets and libraries and servers and packages and so on that make it very easy for even a modestly trained engineer to write a nice-looking web application. And clearly, finally, you don't have to deploy your own infrastructure anymore. You don't have to deploy servers. You can just rent servers from your local cloud hosting provider. So all of these technologies that are useful for many different purposes are really necessary to enable the Internet of Things as an economically scalable technology. Secondly, you can look at the Internet of Things as a natural evolution. This is not some surprise. We've been on this trajectory for a number of years. So I'd use an example of something we're all familiar with, just a basic lock. Started out mechanical. Maybe 15, 20 years ago in some cases, we added electrical functionality to the lock and maybe some very rudimentary, maybe RS-485 or some USB connectivity to the lock to program it in some way. So you could have a key code in it, or you can add a swipe card or make a RFID card that was connected through a serial port to a controller to the door. And so it's not surprising that if you can add network connectivity to the same device, you suddenly have the same device being an Internet of Things device, even though it's really just a small step that you've made beyond the electrical version of a device. Thus, we can think of the Internet of Things if we want to predict what the next kind of devices and services are going to be. All you have to do is you have to look around and see which devices are currently electrical or mechanical, and where would it make sense to add network connectivity to that. For example, given today's circumstances, I wouldn't be surprised if in not too many years, we'll actually have, instead of this rack full of equipment in the back of the AV room, we basically have a single processor that does the audio processing and maybe an amplifier, but everything else will just be connected to an Ethernet cable or maybe wireless altogether. It's starting to happen as well. So instead of having these specialized serial or dedicated digital or analog connectivity, these will, at least in many cases, migrate to a Ethernet IP-based environment. So, however, when we talk about the Internet of Things, there's really two components, the thing part and the Internet part. I believe much of the value is going to be on the device part. The Internet part is the value add, but from a technical perspective, often it is pretty simple. Much there, it's HTTP, it's IP, it's all the stuff we know if we take a networking course. Not really all that exciting. important. There are lots of challenges, which I'll be talking about as I go forward in my presentation here. But the whole point of having the Internet of Things is we reuse what we already have. So one way to define the Internet is really that we have software-controlled networked devices. So these really three components. Software matters, network matters, and clearly we're talking about devices, physical things that we have. So what are some of the challenges that we collectively, as an engineering community, as a policy community, as a software community, will have to address? One of the principal distinctions between kind of old internet devices, your smartphone, your laptop, your desktop PC, is that almost all of the devices that are Internet of Things don't have a user interface. They typically do not have a keyboard. They typically do not have a display of any size, maybe a very small one, but not terribly large. So that means usability is almost exclusively external, namely to a web interface, for example, or an app interface. And in particular, and I will be getting back to that several times, is security is really hard because all of our existing security mechanisms assume that we have a device that we can log into, that we have an account in, that we type in our password, that we have a configuration file that we edit, and to credential that device. You think of your smartphone, you think of your laptop. If the keyboard doesn't work, the mouse doesn't work, it's essentially useless. The other challenge, because these devices aren't terribly useful all by themselves. They're really only useful as integrated with other services and devices. They're really only useful to the extent that they're part of something larger, not just by themselves. And so APIs, protocols of those sort, to make that information accessible beyond a single application is really important. And finally, most of the value will be in the software. Hardware is important. We need to design good sensors, good actuators. We need to be reliable, power efficient, all of that. But the biggest challenge is to design software that is actually secure, easy to use, scales well, and some of the other pieces that I'll be talking about as I go forward. So let me talk a little bit about what I believe the Internet of Things is not, or only in a secondary way. So I'll be using kind of primarily the term Internet of Things, but you often hear two other terms, and I won't go into those because they're somewhat different. There used to be talk about machine-to-machine communication. That really is not a good term because in many cases, there's not really a machine that's doing the communicating. It's a device of some sort of sensor, and they're really talking to a human in the end. That's the controlling factor, not so much another machine. And the other term you sometimes hear, and I don't know if it's as common in Malaysia, is the cyber-physical systems. I won't go into the great distinction debate here, but one notion is that cyber-physical systems are typically systems that have a very time-constrained control loop that is a control system that you might study in electrical engineering of a kind of input control algorithm, output type of model that we used to do by just a control theory type of linear controllers, programmable controllers that you would have in a factory settings often. The other thing that I believe is, I won't be talking much about that, although some of that applies here, just some of the constraints are a little different. I don't think the Internet of Things, despite what you read in kind of more of a popular press, is just about kind of consumer devices. I don't think there's that much interest in having many of the devices in the home be replaced by Internet of Things devices. Often the stuff that we have at home works quite well. It is simple, it's easy to understand, you don't have to worry about debugging the system, it doesn't need a network connection, you don't have to buy a subscription. All of these things is, light switch is not something that most people have a burning desire to replace by something else. I also believe, despite what when people say who are very interested in 5G, that cellular networks define the Internet of Things. Most of the devices on the Internet of Things will not be on the cellular network. So you sometimes hear people talk about, oh, we'll have billions of devices and the Internet will collapse and all that. I don't think that will happen. Simply because most devices won't be visible on the internet directly at all. They will be in a home, behind a gateway. They may have an IPv6 address, but they don't directly count, so to say. They don't have routing table entries. They don't communicate directly to a cell tower, all of that. They're just behind something else. Most of these devices won't necessarily be energy constrained. And the reason for that is because most interesting stuff that does something uses energy. It controls something. And that typically means it controls something energy producing or energy generating. Car, heat, lighting. And in almost all cases, that means it has access to energy because it's in a car, it's in a light switch, whatever it happens to be, in a building controller. So. Many of these devices are not at all a cost constraint. Now, cheap devices help because they make it possible to build lots of them. But many of these devices and services are built into very expensive equipment. Ships, planes, cars. So adding whether the device costs $20 or $40 doesn't really matter all that much when you build a $10 million ship or something. So in that case, again, cost matters, but only as a second order consideration. So you don't always have to use the smallest microcontroller that you can find, a $1, $2 microcontroller. You might use that in your toothbrush because it's very cheap, an electric toothbrush, or your razor, or whatever it happens to be, but you don't need to use that in many cases. And in those type of simple consumer cases, they don't need to do a whole lot. They just measure a few, one or two sensor data points, and that's it. And importantly, and I think that's very important for how we design these things, is almost all of these applications are not necessarily designed by network companies. They're not designed by carriers, they're not designed by IBM, they're not designed by large corporations, but they're often designed by very small companies that work in a particular niche, agriculture, tourism, energy production, whatever it happens to be. And so whoever builds those understands, say, drilling for gas very well, but they're not network engineers, they're not software developers in the classical sense. And they're part of other products, so they are not necessarily something that stands alone by all itself. So let's look at where does IoT actually make economic sense. Like I said, I don't think a household is the best example, although that's much of what we've seen the startup, at least in the US, doing. And I've categorized it into kind of 5 broad classes. So the first one is where you want to automate the extraction of data out of your environment. So your many services and devices, their main function is get data out of the environment, collect it in some way, and use it for something else. So think of this as health monitoring is a well-known version of that, but cars, particularly if they're part of a fleet of cars, commercial, could be taxis, could be delivery vehicles, could be commercial vehicles that do some kind of function, like a clean street or something, or not probably presumably here, snow plows and where I live. What you want to do is you want to figure out where are these vehicles, how well are they functioning, is the driver driving too fast, are they braking too hard, meaning they're probably not a good driver. Those are the kind of things you want to measure. And you can do that manually, but it would be far too inefficient to write it all down and or to stick a USB memory stick in there, get the data, and then collect it all. Metering, gas, electricity, all of these type of classical examples where the main function is simply get boring data out of a device, collect it, and do some analysis with it. It's not a control loop, except at the very long side, namely the control loop is with bad driver goes for data, bad driver gets fired. So the other piece is remote maintenance. So that's more actuating things. Namely, you want to have machines or things that are out there that you want to monitor and possibly see if you can fix minor problems. So for example, you might have a vending machine for drinks, you might have home appliances that you want to monitor and control, cars and trucks again, trains, pumps, all of these type of devices that are generally quite reliable. So they don't have a problem for 10 years, but you want to find out early if there is a problem so that they don't break down. So if they start making funny noises or if they're not performing as well as they used to, often that's an indicator that you need to replace a part or something. The next step is that you have devices that used to be mechanical or electrical, but that they can function better by incorporating additional information, either environmental information or just general internet-based information. So you can think of, again, if we take a thermostat, probably more in a commercial setting, maybe you can use that to control temperature based on the cost of energy. So you might, if there's like electricity shortage somewhere, you raise the temperature somewhere. Or you use occupancy, like the swipe sensor that you have at your door. You know how many people are in the room, so you might be able to detect that you don't need to turn the lights on. Traffic lights, you might sense how many vehicles there are and so on. The last category is what I might call software-defined mechanics. So these are things that used to be mechanical and are now just made electrical and network control simply because we make them easier to manage. Now clearly these categories overlap and are cleanly distinguished, but I believe many of the devices and actuators that we have fall into one of those categories. So one of the concerns that many of us that work in the US and Europe have is we sometimes refer to those as first world problems, namely problems that rich people have, relatively speaking. Like a network doorbell is really not solving any urgent humanitarian problem. It just makes it slightly more convenient to ring the doorbell. But I do believe that they are beyond kind of initial set applications that can be quite helpful in primarily, again, by saving maintenance costs and by making things more reliable, particularly when it is difficult to have expertise locally to maintain things, which is often a problem in countries that are still developing the infrastructure. Another example, I won't talk much about it, but I believe it's kind of one of these probably unintended benefits of these type of generic technologies is that you can develop those to assist people who have disabilities of various sorts, that have motion restrictions, that are blind or that are deaf, simply because they can use now cheap technologies that were developed for something else. The problem, and I work in that area a little bit, is that it's usually the number of people who need that type of technology is very small, relatively speaking. They're not a large market. So companies generally don't develop products for people who are deaf or who are blind or who have motion restrictions. And so in those cases, having generic technology that you can adopt very easily to assist people with disabilities is a real advantage. As one kind of a illustration, if a somewhat odd one, of the kind of services that the Internet of Things makes possible, but which are really specialized. Let me talk about something I read about in a magazine a while ago, namely the port of Rotterdam in Holland. It's a very large port, the largest freight port in Europe. They have, as many ports do, they have a rat problem. Rats like all the stuff that's out there, and they have rat traps. So some poor fellow had to, probably a bunch of them, every day had to go to all of these rat traps and see if a unlucky rat made it into that trap overnight. Not a particularly great job, but somebody had to do it. So what they developed was an internet-connected rat trap. So they would have a sensor in there that would alert the maintenance crew when they needed to take care of that particular trap, and they would have a display on the map that just all the rat traps that needed to be taken care of. So again, that was, well, again, not a large market, but for that particular application, quite helpful. I think it's a good illustration that we'll see lots of these little niche applications that are really, really specialized, are not sold by the millions, but because you can take existing stuff, mechanical stuff, trap, some wireless transmitter, some programmable, like a Beagle board or an Arduino or some similar type of simple microcontroller, and with a little bit of software, you've now created a new product. Now I'll transition a little bit from a generic description of Internet of Things to kind of some of the problems that we need to solve. I'll start at the bottom. It's a little bit of like a protocol stack that you might have seen if you've taken a networking class. So the physical and MAC layer, some of the network protocol issues, some of the applications that we need to deal with. And then importantly, security, which I believe is probably the single most important issue for the Internet of Things, both broad adoption and obviously to avoid causing more problems than we're solving. Issue of how do we perform computation, and for some applications, probably not the rat trap, privacy issues. Let me, however, before I get there, make sure that we reflect a bit on what we can learn from about 40 years of Internet history. I won't go through that in great detail. It's a longer talk that I sometimes give, but it's important to recognize that if we want to build the Internet of Things, we should hopefully learn what some of the things that we've learned, sometimes the hard way, in the Internet space. So the Internet really, we talk about the Internet protocol, IPv4, IPv6, but that's really only a very small, important, but very small part of why the Internet became successful. What made it successful really is this toolbox of protocols that you collectively could use to build application fairly easily without being constrained to what somebody had designed ahead of time. So it's really to think about not just that this is about IPv6 connected devices, it is about devices that speak other Internet protocols, DNS, HTTP, and so on. The other one, which was probably the biggest conceptual and philosophical break from classical telecom, was the classical telecom voice and cellular model was that you have very expensive equipment, but you only have one of it. So you have one transmitter or one switch and telephone switch, and you make it really, really reliable because you don't have an alternative. In the Internet world, one of the lessons was that reliability, as you know if you've taken any reliability courses, is the probability of failure if you have two independent devices is just the product of the two reliabilities. So you can actually get very high reliability even if each one of those components fails relatively frequently. But cost is only additive. So you only, if you have two of them, your reliability goes way up, but your cost is only double of what you had before. Often it is much more expensive to design really reliable single components in that because it's just, you have to take care of lots of special cases. You have to make sure that they're not single points of failures and all that. I don't know if any of you have worked on this topic, but quality of service is clearly one of these evergreen topics that everybody who's networking talks about. The Internet really, compared to the classical telecom world, has illustrated that often everybody likes quality of service, but we can often get by for relatively poor quality of service, and what we matter is really on an average basis the quantity of service, ubiquity of service that we can get. So instead of having a constant level that you have in voice services, or constant bandwidth of 64 kilobit, it's much more useful to have a few megabits even if you can't have them all the time. The other kind of observation, and this is, you get a lot of discussion at the conference that I attended. We had a panel discussion that I wasn't part of, and there was this three panelists on the stage. They had to be restrained by the moderator because there was the 5G folks that said, oh, IoT is going to be using narrowband 5G. No, and you had the Sigfox group, in case that means anything to you, said, no, ours is the best technology. And no, Laura person said, no, you don't know anything, it's our technology. I think that's a particularly unproductive discussion to have, because the internet has succeeded by essentially saying lots of wireless and wired technologies are all fine. Some are better, some are worse, some last a long time, some disappear. But what matters is that they get abstracted at the higher layers. So you don't care anymore whether this is Sigfox or 5G or Ethernet or Wi-Fi, whatever else you have. As long as it has an IP address, as long as it has a domain name, you can combine different devices. So you don't have to get into an argument about it. You still have to decide, but it's also now become much cheaper to build multiple technologies into the same system. Next, it's important to recognize, I'll get into that a little bit more, is that the notion that you're going to have application-specific things is largely done with. That you're going to have, we used to have networks, for example, I don't know if anybody dealt with that, building automation control. There's a network called BACnet, which I don't think anybody studies in college, that is used for controlling commercial buildings. So long before the Internet of Things came around, so that you didn't have to run around and turn the lights off manually and so on. Not a well-designed protocol. It was designed by heating engineers, not by network engineers. Specialized, you could only do networking in a building, for building facilities. I don't think anybody wants to design these type of things anymore. That's not a good idea. We don't want operating systems and spectrum and all of that to be specific to an application. And clearly we need to design good protocols. Protocols are important. I like protocols, I like to design them, but programmability matters much more than that. In the end, most people don't program protocols, they program in abstractions, APIs, and so on. As a central component, if there was one distinguishing factor that I would point out that makes the Internet of Things different from the traditional Internet, besides some of the user interface issues I mentioned earlier, is the scale issue. And scale matters at 4 levels. Namely, one is security. We're not terribly good about security, but we're really bad about scaling security. Like I said earlier, in many cases, security consists of adding passwords to a configuration file or typing in passwords manually through web interface, whatever it happens to be. Often we identify devices, for example, in access control lists, by their IP address. That can't be done if you have millions or thousands of devices, even in a building. We need to manage things at scale. We still manage largely individual laptops and PCs and so on. We have identities. We even give them names sometimes, all that. No longer possible. Our management structures are S&P, very much device management, maybe even command line interfaces, routers and hosts have command lines to configure. If you have a separate Linux server or a router, you know that it takes a lot of steps of manually editing files before you have a functioning device, so on. And we have a very poor set of tools for diagnosing performance problems. We can typically tell whether a device is online or not, but we cannot tell why it's not working well. It's usually kind of trying random things and see if that fixes anything. So, for example, we can't typically tell whether when there's a network connectivity problem, is it because there's a Wi-Fi interference problem, or there is a I'm on the wrong channel problem, or is it a access point connectivity problem, or is it a backhaul problem, or whatever it happens to be, or maybe an operating system problem. None of those things we can easily tell, and certainly mechanical engineers and chemical engineers and so on can't. We're not good at naming things at scale. I mean, we have domain names, obviously, but they don't really work well. I mean, you're not going to assign individual, whatever, human names or favorite comic character names to devices, and not scalable. And we program things individually as opposed to by the thousands. We don't know how to do that. Let me tell you some lessons that are somewhat US-centric, because I just happen to know a little bit more about that, where I think we have done early Internet of Things experiences, but we haven't really done them well. So I think they serve as good object lessons in that. So there is the air traffic control system. The US is renovating that system. It's a very old radar-based system to what's called a next-gen system. In that it's a tens of $billion project. The deadline when it's deployed is always 5 years from now. It's like nuclear fusion, it's never now. And so part of the reason that many of those is that it was designed with specialty protocols just for air traffic control, instead of viewing it as an internet application where you reuse existing security mechanisms, existing protocols. We're designing something called positive train control to make sure trains don't run into each other, don't occupy the same tracks when they shouldn't. And again, that's been a multi-year type of process. And they designed a special Wi-Fi derivative. It's kind of like Wi-Fi, but you can't use the same chipsets. They don't use the same frequency, which then meant it cost billions of dollars extra compared to what many of us could probably design if we were told not to do that. And intelligent transportation systems is a big deal for accident avoidance, designed on a specialty frequency, 5.9 gigahertz, with special protocols again. And again, it's been talked about for 15, 20 years. We're just now starting to see deployment. So again, there's lessons to be learned here is not to design specialty systems, but to try to do them generically. I don't know if any of you, I think most of you, if I may say so, are a little too young for that. There used to be in the early 2000s, every paper at the major conferences, not every, but a large fraction of the papers were about sensor networks. That was the big thing in many countries, research organizations, and I believe that was interesting problems to some extent, but it was not recognized, I believe. That was largely a niche application. What happened was that when people, instead of designing intelligent, really smart protocols and really small operating system, they just bought slightly bigger processors. So somebody did an interesting experiment. They took a Raspberry Pi, which costs in the US about $35, and they compared it to the performance of the Sun workstation. And I used to have something like that in my lab when I started out. Sun 20 workstation, one of the really expensive workstation, cost several $1,000s. And the Raspberry Pi was actually faster than that workstation. So, and that thing ran Unix just fine. It's Solaris, a version of Unix. So the notion that we need to have small devices that don't have full capabilities is probably not true. Like I mentioned earlier, the notion that we need to have specialty operating systems is probably also no longer a good idea. We used to have dedicated functions, moving to now an operating system, simply because we now have enough memory and memory management capability to actually run an operating system in that. So we can now abstract things into generic components. So one of the interesting, probably nobody talks about it because it's not as interesting as graphical user interfaces, but I think what made the PC mature was a very simple development. If you remember, or if you've heard from your parents or maybe older colleagues, that if you bought a PC in the 90s and you wanted to connect a new keyboard or game controller or a printer, whatever it was to it, you had to do two things. You had to make sure the wiring was right, you had to print it and put it in a serial port typically, and you had to download a device driver for that particular device on a floppy disk, obviously at that time. And you had to make sure this was probably, if your PC crashed, that was probably the reason it did, because device drivers are really hard to write well. And then what happened, most of these devices were connected by USB interfaces, and they defined an abstract class called human interface device, which could be a mouse or a keyboard, but you could also make a swipe card reader that you use at a door, or a magnetic or a RFID card reader, essentially look like a keyboard or a mouse. And it would work just as well. You didn't have to write a device driver at all, and made the system much more reliable. What we don't know yet, and I think this is one of the challenges for the next few years, is can we define for all of these internet devices simple set of abstractions so we don't have to program each device separately. Just as an example, I've worked with some people in the medical field, and they told me that for every manufacturer of a simple thing like a blood pressure monitor that you would know in a hospital, you would have to write a new device interface because they delivered the same information, pulse and blood pressure, in some proprietary way, so every new blood pressure cuff had new software, which clearly is a very expensive, unreliable way of doing things. Let me talk a bit about some of the network challenges. I'm dividing that into 3 parts. So the unlicensed part is, we know we can use unlicensed, works pretty well, but it was designed for computing devices that you could type passwords into. So how do we authenticate devices that we might not be able to touch at all because they're in the ceiling? How do we manage credentials? How do we make sure that these devices connect to the right access point and not to something which uses the same SSID but is a rogue access point that pretends to be the real one and then does all kinds of bad stuff? For licensed one, probably in many cases we want to use not a single cellular provider, but multiple providers for reliability. If one has an outage, maybe we can keep the other one. Or because of regional coverage issues, some are more regional than others, and so on. At the country level, in some cases below that. We want to also, the current model for billing and charging for these services also doesn't work because monthly fees for devices that only send a message once a month isn't working particularly well. So think of some of the applications that I mentioned, like monitoring applications. They may never send a message. Actually, that's a good thing because it means the device that it's monitoring didn't break. So you don't want to charge for each one of those because it just makes it uneconomical. So sometimes, however, we can use deferrable low priority communication for these type of systems. So in the US, for example, I don't know if that exists here, one of the big advances of electronic book readers, the Amazon Kindle, was that it used the cellular network, but you didn't pay for it. You didn't pay for it except maybe indirectly for the book. But what they did is they used a low priority service on top of a cell network. So when the cell network was idle, it downloaded the book since it didn't need to be instantaneous. And second, when as a facet that applies to both licensed and unlicensed, we need to make sure we can understand how the data that is produced by these devices can be used, and how do we know who that person is in that. Because often for existing mechanical electrical devices, they have very simple access control policies that work quite well. So think of your thermostat that is in your office, assuming you have one. You can change it around, but maybe only within a certain range, so you can't make it really cold or really hot. But the building manager can adjust to any temperature that you want, and can do it remotely. But you can't do it remotely from your home, and that's what we want you to do as a policy. So that's just built into the mechanical electrical system that we built that way. So how do we do that, and how do we express these type of policies in the Internet of Things? One of the interesting things is that Internet of Things itself has very different communication requirements. In some cases, they might only send a message almost never, like I said. Others might only send it once an hour or so, once a day. And in others, it might send it like 10, 20 messages a second, video images, for example, and everything in between. So how do we manage that so that we have likely different networks that do that? So in particular, this will likely mean that we'll often see combinations of networks, namely LTE, 5G type of networks, local, wide area, and then Bluetooth, Zigbee, Wi-Fi, local. And so I like to distinguish 4 or 5 network scenarios which will probably require very different network connectivity. Same service, just different connectivity. So a very indoor, unmanaged type of networks, a home type of one where you just install it. There's no building manager. The indoor, externally managed, so you have a building manager that might not be in the building itself in that. So they're both likely going to Zigbee and Bluetooth, just slightly differently installed. Maybe the building the managed version might use a LTE, 4G, 5G type thing. And then we get the outdoor urban areas, dense population, often in existing outdoor wireless infrastructure. There, something like LoRa might actually work quite well. It typically covers with a small number of transmitters an urban area. Then we have the rural outdoor area, which is much less dense populated, probably no 4G or 5G coverage at all. There we're getting into maybe Sigfox type of technologies, which can cover up to 40 miles or so under ideal conditions when you don't have non-line of sight issues or reflection issues. And then finally, real remote areas where we need some kind of satellite receiver model, like the pipeline monitoring and so on in really remote areas. So we'll likely continue to see, even at the local level, quite a few different networks. So NFC as kind of your network for very short range communication, where you really don't want to talk long distances because that gives you an indication of where things are. Zigbee and Bluetooth, either low energy or ubiquity, and Wi-Fi, just simply because it gives you scale based short range and low bandwidth communication to wider range directional antenna type communication. Whereas Zigbee survives is somewhat less obvious. Bluetooth is now a pretty good competitor, but that's a second order issue. So what role does 5G play? And I won't take a whole lot of time discussing that, and that's a whole separate talk. But believe what you hear about 5G in terms of IoT applicability is largely 2 things, namely the use of millimeter wave spectrum, 28, 10 gigahertz and above type of thing. Not terribly interesting for IoT, I don't think, but maybe indoors in some cases. And low latency, kind of millisecond as opposed to 100 millisecond latency. The 2 applications that I can think that are useful, most IoT applications are not latency sensitive. Your electric meter doesn't care whether it takes a second to read it. Is for intelligent transportation systems, namely instead of having vehicle to vehicle, is to have vehicle to infrastructure to vehicle communication, to deal with range issues and analytics and so on. And that purely often requires for safety applications to have a very low latencies. And another one that might be interesting is alerting for tsunamis and earthquakes and so on, where at least sub-second latency, not so much for tsunamis, I presume, would be really helpful to do. And existing cellular networks don't do that well. But for many of these applications, what 5G needs to provide, and I haven't seen a whole lot of discussion to that, is not just one-one communication, but one-to-many communication. Because you need to alert, for example, a bunch of people in an intersection to make sure that they don't crash into each other. Talk briefly about application protocols. The classical model today is that you just generally have a very small set of things that actually talk to each other. You have an app on the phone, then you have a thermostat and a smoke detector, say, and they do some communicating, but they don't really talk to anything else. Longer term, we need to be able to combine devices that have no idea that they need to talk to each other and make them do things together. Just read because the same custodian needs to know all of these, whatever. Or you can just build interesting applications on that. If your soap dispenser, your refrigerator, your towel dispenser can all communicate in a common way, new and interesting applications might be built. So if we look at it from a building services perspective, one of the challenges today is it's really difficult to find out what devices are actually in your home or in your building at all. They don't announce themselves, they don't tell you what they are, you can access them, all of that. So you have to manually do all of that. It doesn't scale that. We need to be able to do layers of functionality so that, again, like I mentioned earlier, you can allow different functions for different people. You need to be able to delegate that functionality to different individuals. So for example, I need to, just like I do very easily with physical objects, I need to give somebody a key. I tell you, now you can use my office for the day, and then you give the key back. Very easy, I know exactly what I need to do for that. We don't really have that today in the Internet of Things. One of the other kind of observations is that once you start defining interfaces to devices, they tend to last really, really long. Just for fun of it, I collected the history of some of the more electrical, mechanical interfaces that we have in that, as well as some of the more software-defined ones. And you'd be surprised, I was certainly surprised, how long many of these have been around and how fundamental they are. So your electric plug here is, I looked it up, was designed in 1947 in Great Britain after World War II. The US version is actually even older. In that. Internet protocols were defined in 1981. PDF has been around since 1993. So in many cases, 20, 30 years, 100 years in some cases, and they're unlikely to change. Right? Nobody's going to replace all electric plugs. So we need to think about interfaces as kind of these long-term constants. Everything else changes. But these interfaces, a small number of those, stay constant. The next problem we need to solve is we don't have a good answer how just to simply name things. We need to name things in order to program them. So we know how to name interfaces, MAC addresses, IEEE addresses. We know how to name network connectivity, IPv6 addresses. We kind of know how to name devices, but like a domain name, for example. But the domain name system doesn't really reflect well the difference between ownership and current use, because it uses domains that might be based on the manufacturer or the current owner. Often what we really want is something that is more descriptive. So for example, I want to specify a light in a specific room, not what the MAC address is, because that changes when I change the light bulb, but where it is and what function it has. In the Internet Protocol world, we really only have a small number of communication identifiers. We have two types of URLs, namely ones that you own the domain name for, and we have ones that are owned by somebody else, like Google or something like that. And we have telephone number, E164 identifiers, and we have service-specific ones that are proprietary, like your Facebook handle or something like that. They all have trade-offs, but none of them seem particularly well suited to the Internet of Things. So there's probably a need for defining something that is a bit different in that. Ideally, we would like these identifiers to define not just a single entity, but maybe multiple. We want them to be portable so I can change network providers without reprogramming systems, etc. Again, like I mentioned earlier, protocols are important. There's still some protocol work needs to be done, but nobody wants to program raw protocols. Indeed, you could argue that the advances that happened in networking actual use weren't new protocols, but they were actually things that allowed people to program services. So the Socket API, for example, the Java network APIs, PHP and similar web languages, frameworks like Ruby on Rails early on and the ones that followed, those really, in each case, probably by a factor of 10, increased the number of people who could suddenly write software, because it just became easier to do than it was before those existed. And we need to, if we want to have Internet of Things devices that actually get popular, the most important part is to design things that programmers love, not hate. We've done not a good job. I've done a lot of work in voice over IP, where people design really complicated APIs that nobody likes to use, and then they just don't get used. And like I mentioned earlier, most IoT programmers won't be software engineers. They'll be mechanical engineers and so on. I think there's a generic architecture that, independent of a sensor, we can use, where we have a set of interfaces, and we don't quite know yet what these are. So for example, there's a sensor markup language called SendML. We have a cloud processing language. We have an access control problem that I mentioned earlier. We have user-delivered code that does specialized functionality on top of the basic one. We need some data storage. So these are all pretty generic components. So essentially what we need is an operating system that not just at the Linux level, but at the higher level, that provides these functions, because they don't depend very strongly on whether you're monitoring a pipeline or you're monitoring health of somebody. Finally, in this section, I wanted to just point out that we think of Internet of Things as small processors with built-in sensors. But your phone, your smartphone, is an Internet of Things device because it has a bunch of sensors in it, it has network connectivity in it, and it can do things without your user interaction. So we should think of integrating those devices because they can provide additional data points. And in some cases, there will be virtual devices. This is a prototype that we built in my lab, for essentially pretending that things that actually are gauges and physical sensors, make them virtual so you can test things and display things. One of the important pieces to consider as we design Internet of Things devices is that it will live much longer than your smartphone. Smartphone you might replace after 2 or 4 years, but Internet of Things devices might live 20 more years. In computing and networking, we don't have a terribly good record of dealing with that. I give it as an example. Windows XP had a life cycle of about 13 years total from beginning to when it was taken out of service. You still see a lot of Windows XP devices out there. They're no longer secure, they no longer get updated, but they never had a model to transition themselves to a new operating system. More recently in the US, a manufacturer of Internet of Things devices was founded in 2012, sold devices for $300 or so from the home, and then in May this year, they said, well, we're no longer interested, we got bought by somebody, by Google, and we're doing something new and different, so your device will cease to function. It's just now a piece of plastic with an LED in it that blinks or something. And that you spent $300 on that, that's your problem. So that is a model that if it were to do that for cars, people would consider you completely irresponsible, you'd probably get sued, whatever. So just as a comparison, a 20-year-old Toyota Corolla, which probably still drives around in many places here and elsewhere in the US as well, is still safe to drive, still works somewhat if it's not too rusty, and you can still actually get money for it. It still costs in the US about $2,000 to buy it. Right? So it still has value in it compared to what it did. This also matters for internet connectivity and network connectivity. Cellular life cycles are roughly on the order of a decade or so in that, but the network itself typically lasts about 20 years. And this has been true for 1G, 2G, for 4G, et cetera. So we need to think of as network interfaces as well. That's actually a problem. People build 2G interfaces in it, and in many countries, 2G is being decommissioned and reformed. So how do we do that? Deal with these devices that still need to communicate. So we need to think of a life cycle model for Internet of Things devices. So we'll have probably multiple phases where you have active support, end-of-life model, and you might need to think of essentially having a designated custodian, just like, I don't know if it's common in Malaysia, but in the US often parents, this is particularly true in older days when mothers often died in childbirth, they would designate an uncle as the person who would take care of that child if the parents were unable to. So you have somebody ahead of time that is designated as the caretaker. And maybe we need a version of that for Internet of Things devices so that you have some assurance if you pay lots of money for a system. And I'm not so much worried about systems in the home, I'm worried about building systems, for example, that somebody will be responsible for that. We also need to have an economic model. In many cases, it's not even clear whether you actually own the device in any meaningful sense. Namely, if somebody can turn off a device remotely on you, you don't really own it, you're just renting it. You just don't know for how long. We need to know, and this is as much as a regulatory and consumer protection issue, is what is the expected lifetime of a device? When I buy something, I can't expect it to live 100 years, but should I expect it to live 20, 10, 5? That matters. And who pays for computation and storage? I buy it once, and then do I get services for 20 years or not? How do I pay for that? And the problem leads, in many cases, into privacy being essentially the goods that are being sold, because people aren't willing to pay monthly fees for everything. We talked briefly about security. That's obviously a much bigger topic. So we've had problems that open source implementation have developed risk and vulnerability after many years, which people never discovered until somebody looks very closely. So how do we update devices? For electrical devices, we have something called Underwriter's Laboratory. I don't know if that's used in Malaysia as well, but I'm sure you have a safety laboratory. If you sell an electrical device, a hairdryer, a toaster, an oven, it has to be certified that it's electrically safe. It might not work well, but at least it's safe. So how do we deal with that in the Internet of Things security realm? Do we need a security certification system, testing system, because many of these existing devices, if you follow that, are very poorly designed in any number of ways. How do we enroll devices? Think of a new building, like yours, since you just moved, I mean, for those of you who work here, moved in here just whatever, a year or two ago, and if you think of all these devices, every light bulb, every smoke detector, every door, being a network device, as it will be, maybe not in this building, in the next one, then you don't want to program the network password into each one of these devices. And it's going to be a pain the first time. Imagine changing it, because it's a good idea to change passwords. So we can't do the one device at a time model. It just doesn't work well. So how do we do that? How do we get device passwords in there? We're working, in my lab, working on techniques that allow you to do reverse the model so that you can do that in a whole bulk of system. Privacy clearly is for many systems, not so much for some of the public-facing systems, but for building systems, medical systems, is probably the single most important facet in that. This is probably more US-centric cartoon. I don't know if any of you've seen it, but we see an old cartoon is on the internet, nobody knows that you're a dog, and that's no longer quite true. The Internet of Things really has, from a privacy perspective, three kind of device classes. And we have things that are public. Nobody cares if somebody reads it. You don't want to write to it necessarily, but think of a bus display that shows when the next bus or train arrives. That information is public. If somebody reads it, that's actually a good thing. Then we have semi-private devices, so that might measure temperature in a building. I don't really care if people read it. I don't want people to change it. and maybe not everybody should read it, maybe only every employee or something like that. And we have private devices that clearly only a very small number of people should have access to, medical, security-related things, and so on. Recently, a US agency, kind of one of your sister agencies, if you like, of the MCMC, NTIA, did a survey of consumers and about internet usage. And a very large number of people said that they're using the internet less, not IoT, that wasn't part of it, I'll get to that. Don't use the internet as much as they would otherwise because they fear identity theft and other bad things happening. And this has been, will continue to be a problem for IoT. Another survey, which was done a year ago, said about half of the users are uncomfortable with the device security that we have today. I believe one of the ways we can address security, besides having good regulations and having good economic models, is that we do much more of a processing locally as opposed to in the cloud, so that you know that the data never leaves your household or building, instead of being sent off to who knows who for what purposes in that. And with that, I'll conclude. So what would I see as some of the guidelines for people designing both individual systems as well as broader systems? The first guideline is a general good internet design principle, namely, we need to design simple systems that are reusable in general, because you never know what people will use those systems for. And the more general they are, the more useful they will be, even for things that we didn't anticipate. Performance will take care of itself. Once bandwidth gets cheaper, computing gets cheaper, memory gets cheaper. That also means designing for surprises. You just don't know what people will want to do with what you designed. So you have something that you didn't anticipate. For example, many of the networks that we have, 2G, 3G, 4G type of networks, all of them, and there's a separate discussion, are used in ways that the designers never anticipated. SMS, for example, was never designed into 2G, that just happened. And we need to design for layer 2 evolution, because there will always be new layer 2s, kind of lower layers in networking, both locally and wide area, 5G, whatever. And we need to coexist with multiple of those, because there will be no single winner of that. And with that, I appreciate your patience and interest, and gladly take questions or comments that you might have at this point. Thank you very much. Any questions? I don't know if you can, we don't have a microphone, so you have to shout a little bit. Yes, please.
You talk about standardization.
You're raising a very good point, namely standardization. And I do believe that there is a role for a number of different kinds of standards that we just don't have, particularly in the data representation area and the security area. And those would, there are others that you need, but those would probably be the two biggest ones that I can think of, simply because right now every single device represents data differently, and we don't have good security standards as to what you should do, and also some of these kind of provisioning systems are all done in a proprietary way, which means if you have different manufacturers in the same building, the same vehicle, like large commercial vehicles, like ships and planes and trains and so on, it gets really difficult to integrate all of those different manufacturers into a single system, or factories is another good example in that. So yes, I think standardization, and there are plenty of organizations, but I'm not seeing any of them. They all do these frameworks and architectures and all of that. I don't think that's what a big problem is, because they tend to make things more complicated. We don't want to recreate the IMS and 4G architecture where you have, I don't know, 50 labeled interfaces. I think we can do it much simpler and in more modular way, so you can pick the pieces that you need. You don't need Wi-Fi authentication if you're not using Wi-Fi, and you don't need some other pieces depending on what you're doing. So the internet model of doing kind of building blocks that you can assemble as you need seems to me a really important one. So thank you for bringing that up.
Any other questions? Yep.
You mentioned just now that when you have this IoT, about 10% of it will be running on the mobile,
Yep.
while the rest will be maybe license spectrum or whatnot.
Yep.
So the question is whether there are studies being done to 90% will be running non-mobile spectrum or non-mobile service. Any feature or spectrum that you need
Right.
unlicensed for
Yep. And that's a good one. So, and obviously, as anybody who works for a regulatory agency, the first thing you hear from people is, I want more spectrum. I mean, that's, you can count on that. And I would actually argue that, generally speaking, because many of these applications, with the one exceptions of remote cameras, they obviously produce a lot of data, is what you'll see is that let me try to answer two somewhat implied questions. I mean, one is, the 90% versus 10%. To some extent, that will depend on, or to some large extent, on the economic model. So what you start to see, and this was an interesting test case, is, and I don't know if this applies as much in Malaysia as it does in the US, is it used to be that everybody was really excited about having Wi-Fi everywhere. I mean, in your coffee shop, in your bus, in your train, in a hotel, and all of that. And it was because cellular data was so expensive, or very slow for that matter. So Wi-Fi was both cheaper, generally speaking, and faster. That has changed, at least for many people now. I don't really care as much because if a hotel wants to charge me for Wi-Fi, which some hotels do, it's usually a more expensive hotel, they're more likely to charge you, I just use my 4G, and I'm not going to do video streaming, but it works well enough so that I'm not going to do that. So I would actually argue that the cellular providers can get more than their made up 10% if they make it sufficiently cheap to do that. If they don't make it sufficiently cheap, then there's actually, I think, a higher likelihood that you have other entities named either unlicensed, and this could be unlicensed in building, or it could be using unlicensed spectrum. So the one interesting spectrum model that I think is actually might be an interesting idea to pursue, and we're starting to do that at the FCC in 3.5 gigahertz, which isn't quite the right spectrum for that, but the model is similar. So a likely licensed model, because many of these type of IoT applications are naturally well behaved. They don't, and again, leaving cameras alone, they don't produce a whole lot of data. And they send data relatively infrequently, and often they're not sensitive to latency, with exceptions. And so you could imagine a spectrum that has good coexistence properties with wide areas. So one area, and I'm not speaking here, and this is not a plan of any sort, but I believe some of the public safety communication moves to cellular, that some of the low-band spectrum, like 400 megahertz, for example, might actually make an interesting, lightly licensed type of registration-only, coexistence specified, so be nice to each other type of spectrum that wouldn't be dedicated to IoT directly, but IoT would probably be the single most important use, simply because it wouldn't be useful for anything else. It wouldn't be useful for cellular, there's not enough bandwidth there in that. So that, because I'm just seeing that there is a gap there, that Sigfox and Aurora use 900 megahertz in the US, at least I don't know what we use elsewhere, and that spectrum just is pretty crowded, and there just isn't enough of it, and they seem to be societally valuable. So yes, I don't see much room for dedicated spectrum, but there might be room for a new model which just happens to fit unlicensed, lightly licensed model that fits well for low data rate communication. Thank you so much. Sorry for the delay, but thank you for sticking in there, and I'd be happy to talk to anybody individually as well afterwards.
Thank you, Prof. Henning, for a very fruitful lecture on this topic. I think maybe I would like to, as a token of appreciation, we would like to pass something to you.
Thank you so much.
Thank you. Thank you for your time. Okay, I think that's all for today, and have, as usual, our tea served outside. Please serve yourself.
It's kind of funny that